throw toilet paper in the toilet because they clog. Try to use the bin that is next to it. Here in Brazil, I think it's a problem. So please don't try not to do it, or try to remember not to do it. On a second note, we Alejandra Castro will begin the evening session.
Let's talk about toilets.
It was a very important. It's a very important notice. Thanks, Ale. Take it away.
Sorry, I forgot to write down here. Okay, sorry, I'm almost done. I'll start saying interesting things in a second. Okay, good. So last lecture, we were doing this analysis of non-perturbative solutions of AdS₃ gravity, where the lamppost solution that I wanted to show to you, because it's so famous and well known, it was the BT-SAT solution. And so we discussed various properties of that solution. We started a discussion of it in Euclidean signature, but there were also some Lorentzian properties of it. And for instance, in the Lorentzian signature, we saw that it complied with our boundary conditions. And in terms of the charges that we defined, this is a solution that would be a non-trivial solution just because it has non-trivial values of its charges. Also compared to global AdS₃. So what was the value for global AdS₃ of mass and angular momentum? Very good. So therefore, global AdS₃, from this perspective, is not the same as the BT-SAT solution. They're different solutions. They're related by a diffeomorphism, not surprising, because everything in pure gravity is a diffeomorphism away, but it's a large diffeomorphism, therefore it will correspond to a different solution. We also mentioned that it had an event horizon, an outer event horizon, located here at the outer event horizon is located at the surface r equal to r plus. We draw the Penrose diagram, which I won't draw again. And then from the Euclidean point of view, so if you do a Wick rotation of time, the understanding of the Euclidean BT-SAT solution is in terms of a solid torus. And so the way that you understand a Euclidean BT-SAT is a solution that has basically these two periodicities, 1 and 2. And the characteristic feature is basically this parameter tau, the complex structure, which I wrote down here again. Okay. Now, before closing this discussion on classical properties of AdS₃ gravity, I wanted to say a few more things. So the next thing that I wanted to say was also following Chiara, like once you have the solution, a black hole, the thing that you want to describe is basically its thermodynamics. It's just yelling at you, please say things about the thermodynamics. Of BT-SAT. And yeah, so we basically have here, that's also why I recapped this information here. So we actually have extracted all the quantities that we need to describe its thermodynamics. So we know that the solution has some mass and some angular momentum written there on the board that we computed as charges. But now from this Euclidean picture, we know that Euclidean time has a non-trivial periodic identification, which is going to be controlled by this parameter beta, and also a shift in phi that is going to be associated to an angular potential. So to each of these variables here, so for m, we'll have a conjugate variable, which I'll call TH, so for Hawking temperature. And the Hawking temperature in this notation is basically, so let me write it like this. What I call here beta is basically the inverse of TH with a factor of L, just because of how I'm picking units. And the conjugate variable to the angular momentum is going to be the angular velocity. That's also why I call it omega h. And it's this quantity that appears here in the definition of the killing vector that defines the killing horizon. Okay? Then the next thing that we need, so this will be the temperature of the black hole, and this will be the angular velocity of the black hole. So then we can also associate it to the solution, some entropy, the Bekenstein-Hawking entropy. It's kind of funny. In 3D, BH can mean like 3 different things. Can mean black hole, can mean Bekenstein-Hawking, and it can also mean Brown-Hinault, which is the thing, like this value of the central charge that we got. In any case, so I hope from the context it will be clear how BH is being used. So in this case, it's basically pi over r divided by 2 times g Newton, okay? Which is, again, this I'm writing just basically the area of the horizon divided by 4 g Newton. The area here is just the length of a circle, and so that's the formula. And something that you can check quite in a quite straightforward way is that dm th is equal to omega dj. Okay? Now, yeah, that's it. Yes? Is a conjugate variable to the mass in the statistical mechanics sense, the Boltzmann sense. Like, so in the sense of like when I define the microcanonical ensemble, or in the sense, yeah, that like when you define a partition function, it's, no. Well, sure, but partition functions are sums over energy eigenstates of e to the minus beta e. So what you put up here in the exponentials are the conjugate variables to each other, right? And so if I add angular velocity, like, so then these are the conjugate variables to each other. That's what I mean by conjugate, yeah. Yeah, so if you want, you can put this th over here, and then it will be beta, and then it will be basically the same thing that shows up in the Boltzmann factor. That's what I mean by conjugate. Okay, so usually when you do thermodynamics, like there's no such ensemble where M and T are held fixed, right? There's the microcanonical ensemble where the energy is fixed. There's the canonical ensemble where the temperature is fixed, but the energy is allowed to vary, and so forth, right? So they're conjugate variables to each other, and it's from that point of view StatMech. Okay, so that is the entropy of BTZ. And now what I want to do, I also wanted to connect to the phase transitions that Chiara was talking about. So I wanted to not just leave the thermodynamics up to this point. All right, I'll erase this. Let's do the following computation, because this is also going to be useful as we move on to the quantum part. Let's discuss basically actions and free energy. In these situations, okay? So what I want to do is, given the set of solutions that I have, I want to be brave, and I want to basically consider, like similar to here, so I want to define basically some type of partition function for my system, Okay, so where a dream would be that this partition function, as we were just saying, will be something like some sum over energy configurations weighted by an appropriate Boltzmann factor. But I don't have a luxury of doing that yet. So what we're going to do is basically think of this. So I'm going to think of this partition function. Of course, it's a function of beta. And I'm going to follow the principles of Gibbons and Hawking. From the 70 and say, look, this partition function at finite temperature should be understood in some sense as a path integral over metrics weighted by their Euclidean action, where the temperature enters as a boundary condition. I'll write it like this schematically. So I'm imposing that I'm going to be doing an integral over all geometries that will have some fixed value of beta, okay? And in this context, from this Euclidean point of view, this will mean, okay, all the solutions that you have where beta is hold fixed. And we know how beta enters in the geometry is basically a periodicity, okay? So you're going to be summing over all solutions that have that same periodicity, okay? Of course, this is a very difficult computation to do, so following Gibbons and Hawking, we'll take a semi-classical limit. Because I don't know yet how to, we will discuss how to sum over all metrics, but what we're going to do is just say, look, just consider the classical solutions to the equations of motion, and weight them by their action, okay? So sum over all the solutions that have a given value of beta and weight them by their appropriate action, okay? So maybe I should write here, it's an approximation, because of course there will be corrections. Okay? Good. So in this discussion, then, I would say, okay, so what I have to do is consider all of the solutions that like have some fixed value, and also maybe here at this stage, you can of course generalize this. It doesn't just have to be beta. You can consider all the solutions that have some fixed value of beta and omega as well. Or if you want to write it in a bit more fancy way, you can say all the solutions that have some fixed value of this tau. So tau, again, is a complex variable. So I'm writing it as tau and tau bar. Yes? Oh, so this is where I'm taking just a semi-classical limit. So I'm just going to be, so this, thank you for clarifying that. So by semi-classical limit here, I mean that I'm just going to be looking at the tree level value, on-shell value of the action. So there's no ghost, there's nothing quantum. It's just like the leading order effect. We'll talk about the quantum stuff in a moment. So yeah, so I don't have to, I'm kind of like ignoring those, all of those things are kind of like naively, they're subleading corrections, they're suppressed by H bar. And so I'm just looking at what is the biggest effect, and usually the biggest effect just comes from the value of the classical action. So let's just basically do the sum of all the solutions for some given value of this classical action. So, and I write I here just to distinguish, like usually there's a convention that when you write S, it's the action, but without imposing that it's on shell, and when you write down I, it means that you evaluate it on shell. There's some set of friends of mine that like to have that, that convention. So the I is just basically, maybe let's So I Euclidean is basically S evaluated on some equation of motion, okay? Okay. So let's do this. Okay, so what would be Euclidean, if I fix a temperature, what would be Euclidean solutions that satisfy to this exercise? So for instance, we know that we have this solution that will have some value of tau and beta, but we also know, for instance, that so we know that BT₃ or Euclidean BT₃ satisfies the boundary conditions of being, by boundary conditions now I mean this boundary condition, that it's a manifold that will have a fixed value of beta, okay? But we also know of another solution that satisfies that we basically were arguing that is roughly the same as BT₃ in Euclidean signature, which was global AdS₃, right? So the Euclidean version of global AdS₃ is usually what we called thermal AdS₃. The boundary condition. And the difference between these two was basically how you were imposing how you were encoding the complex structure. So if you fix tau for BT₃, then I want to write it as like, so yeah, maybe let me write it like this. So if this guy had some complex structure tau, then this solution had complex structure -1 over tau. Okay? So that's what we saw. And vice versa. You can decide that this one has tau and then this one -1 over tau. It goes both ways. So they're related in that way. Okay? So from that point of view, let's do the exercise of evaluating the action from the point of view of thermal AdS₃. Okay? So I want to evaluate this on-shell action. So of thermal AdS₃. Okay? So evaluating actions is always tricky. It's conceptually is very straightforward, but as you saw, like actions have like boundary terms. You have to add all these counter terms and stuff. So okay, there's always like a little bit of an art. When you're working on a project, always the thing that is like, that someone will like, one of your collaborators will nag you about is like, how did you really compute this action and stuff? And like, how did you do the bulk? I don't know. There's always like some discussion. But in AdS₃, there's a cute trick. And so the cute trick that I want to do is the following. So the way that I'm going to evaluate this Euclidean action is actually I'm going to evaluate the variation of it. Okay, so some of you might be like, that's a weird way how to do it, but I think it's a very convenient way how to do it in AdS₃. So we know that the variation of the action should have been equal to the variation of this, sorry, the equation continues here. I just want to make sure that it goes like this. So remember, Tij was the boundary the tensor that we evaluated before, and this G0 was the boundary value of the metric, right? And the reason why I want to evaluate it this way is because we already have an expression for the stress tensor. So that's why I'm saving a little bit of time. Now, in this thing, so what I have to do here, I want to get, at the end of the day, what I'm trying to get is a function, this is a function of tau and tau bar. And tau bar in the Euclidean geometry is basically encoded, the information of tau and tau bar, when we wrote it It was not written inside of the line element. So remember, the line element was just given by these cosh of rho, sinh of rho. And all of the information about tau and tau bar is basically encoded in the periodicities of the variables. Okay? So what I'm going to do, so the trick is to basically place the info of tau and tau bar in G0 and have the periodicities fixed so that the periodicities are just 2 pi. Okay? This is going to give me a little bit of an easier time because I don't want to have basically dependence on temperatures and the ranges of integration, especially if I try to compute the on-shell action in this way. Okay? So the way that you can do this, so for thermal AdS, you will define a new variable. So you can play around with the coordinates and try to see what would be a coordinate transformation that will do the trick. And so remember that for thermal AdS₃, I was using this variable W to describe the periodicities. So that's why it's the same notation. It's the same W from last time. So we will do this transformation. So this is the Euclidean coordinate for thermal AdS₃. And you can see that basically now the identifications of this variable set tilde are these, whereas omega would have had identifications plus 2 pi tau. Okay, so that's what I mean by like removing I'm going to be removing the dependence of tau on from the identifications. Now I'm going to put it in the metric. Sorry. It's the same. It's the same as this one. Sorry, too many bars. Thank you. Okay, and then the boundary metric now. So before the boundary metric with respect to omega, to respect to this W, would have just been a flat space metric. It would have been very simple. So now the boundary metric will have all the information about what tau and tau bar is. Okay, and so just remember before it would have been just something like this. If you would have written the boundary metric in terms of omega and omega bar, it was just a flat space boundary metric. But now because I did this coordinate transformation, now I'm putting all the information in here in the G0. Okay? So then this means that in this expression, so let's write it again. Tij, because now it's going to also make more sense what I mean to vary with respect to delta Gi0. So now I want to look at how the metric changes if I change the temperatures, if I change tau and tau bar. So from this perspective, it's kind of awkward to see it because tau and tau bar just enter in the periodicities. But from the point of view of these coordinates, the periodicities are fixed, but then I know what it means to change the temperature. Like, it's just explicit. You just take it as variations. And so the final result, and then this integral here is super easy because you just have to integrate you will get a factor of 2 pi and a factor of 2 pi I. So it's just 4 pi squared I. So that's a very simple integral to do. And so the result here will be 4 pi squared I. And then here I'm going to do something funny, so I'll keep on writing. So of course the components of the stress tensor are also going to change. You should be computing the components of the stress tensor with respect to this tilde variables. I should have written it like this. But I'll write it. You can keep track of how it was related with respect to the all variables. And this is the answer that you're going to get, where for thermal AdS₃, and this is also why I'm picking thermal AdS₃, the TW or 2G. So I'm basically, since I'm focusing on thermal AdS₃, you will compute the stress tensor for these values of mass and angular momentum. And that's why I get these negative numbers, and that they just depend on the coupling constants. And so now from here, what I can say, like these things are just like constants. And so if I want to know what is the value of the action, then I just remove the deltas. Right? So that's a trick. So then the action on thermal AdS₃, and maybe I should put also here that I'm doing this for thermal AdS₃. It's just I pi over 12. I hope I got, sorry, yes, I did put the signs correctly there. So that's the value of the action on thermal AdS₃. Okay? Yeah. These tricks are very special to 3D gravity, so if you try to use this trick in higher dimensions, it's probably not great. You just go and evaluate the on-shell action, but this is a cute way how to do it in 3D from this point of view. Okay? Again, there's many different ways how to do it, but I don't know. I find this a very nice way how to do it. Okay? And now, so that's the action of thermal AdS₃. Now, what if I ask you, what is the action of BT set, of Euclidean BT set? Can you get it from this answer? Right. The only thing that you would do is just replace whatever you got before by a -1 over tau. Yes?
Why this trick doesn't work in 4D?
Because you don't have, well, there might be versions of it, but it's not super convenient. Well, the trick actually, sorry, I should take it back. This part will work, and you will be able to compute the free energy or the on-shell action of like thermal AdS₃ in this way. The part that doesn't work in higher dimensions is this arrow that I'm doing here. Because in higher dimensions, thermal AdS is not related to a black hole quantity by like a simple transformation. So this is the special, no, it's good that you mentioned this. So this type of like trickeries of trying to put the temperature explicitly in the boundary metric, you will be able to do it just trying to like get rid of it as a periodicity. But this is very special. This is a 3D sort of special feature. that these two configurations are related by such transformation, by this large diffeom. So that's why you won't see it done in higher dimensions, like, and when Chiara probably, you wrote the on-shell action. Yeah, you wrote for them the free energy. Like, she would just tell you, like, this is the value of the free energy, but like, she wouldn't have gone through the song and dance of like, oh, let's first compute it for the vacuum and stuff, okay? But in any case, so this is the answer. Good. Now, notice one thing though. Although the geometries, so because this was something that we were discussing a lot, although the geometries basically look very, very similar, and they were just related by a change of this parameter, the values of the on-shell actions are not the same. So the on-shell action is sensitive to specifying if you have a solution at tau versus a solution at -1/tau. Okay? Of course, there's a diffeomorphism that relates them. So there was a diffeomorphism that told us how to change tau to -1/tau, but our action is actually sensitive to that. We see it in the action, we see it in the charges, we're seeing it everywhere. So from a Euclidean point of view, you can see that these are different configurations just because they have different values of the action. For some fixed value of tau, they will have different values of the action, okay? So then we go up here. And when you decide to do this computation, so we were computing this partition function, we know that there's going to be two configurations for a fixed value of tau and tau bar. There's going to be actually two configurations that we know about. There will be the configuration, the contribution from thermal AdS, and then there's going to be the contribution from Euclidean BT set. Okay, so I'm summing over the solutions that we know so far, and these are the two solutions that you would say contribute to this partition function. I forgot the set, important. Okay? This is what we know. I'm writing ... because we haven't discovered other solutions yet. Okay? Good, but let's work with this. So those are the two configurations that we know are contributing to this partition function. And let me now take a simplification. So let's write down these formulas, and maybe let's erase some of this stuff here. So now let's consider, we want to study the set of tau and tau bar in more detail, but let's now simplify. But for simplicity, you can do it without the simplification, but I'm lazy. Let's set omega h equal to 0. That basically means I'm going to be setting R minus to 0. I'm going to look at things that are not rotating. Okay, so let's just look at set as a function of just beta. And from this point of view, let's write down then the actions. So this I of thermal AdS₃, so will just be -1/12C times beta, and I of BT set of 1/beta. Okay? So recall that tau in this simplification is just I beta over 2 pi. Okay? That's the answer that I get. Great. And so then, to be explicit, so then set of beta, again, which is I of thermal AdS plus minus I of BT set. Okay. And what I want to do is see what happens to the free energy of this system. So this partition function, I'm going to interpret it as being equal to e to the minus beta times f, okay? Where f is the free energy. And so what is this thing telling me here? So I'm trying to, like, again, it's this is the AdS₃ version of what Chiara was teaching you in higher dimensions. What we have in this situation is that for a given temperature beta, there's two solutions contributing to your free energy. And so the question is, which of these two exponentials is more dominating? It's dominating, basically, for given values of temperature. So you would tell me, for instance, so, oh, sorry, I shouldn't have erased that. I don't need to write it up here. So now the question is, to F, okay? And so we have here how this free energy, how these actions basically behave as a function of beta. And so you can first say, okay, let's just take limits. So let's say that for beta going to infinity, so what is beta going to infinity? That will be low temperature. So if beta is going to infinity, which of these two things is bigger? Or sorry, or smaller, yeah, well, doesn't matter. So this one is more negative, right? So I thermal is less than I of BT set. But this will tell me that then when I do e to the minus ITH, this one is bigger than that one, right? And then if I take beta going to 0, which is high temperature, it's the opposite. I of BT set is going to be less than I thermal, and I'll have of I thermal. And at beta equal to 2 pi, what would happen in this formula if I put beta equal to 2 pi? Both free energies are exactly the same. So from this point of view, what's going on is that if I now plot the free energy as a function of temperature, it's nicer to plot it as a function of temperature versus as a function of inverse temperature, just because it's a little bit more intuitive. What's happening is that at low temperatures, I have a value of the free energy that will be given by C minus C over 12. So remember, the free energy has a factor of beta here. So it's just the C/12 that I have here. And basically, for low values of temperature, this solution will be the dominant contribution to the free energy. And then I'll hit a temperature that will be 1/2 pi. And what's going to happen at this temperature, after this temperature, is that I will favor the BTZ free energy. And the BTZ free energy basically goes like it goes like temperature square, and it will have like this parabola like this, okay? And so this point here, what is that? Now we are all expert. Come on, you can do it. It's a phase transition. Yes, of course. Don't ask difficult questions, right? So this point here is the version of the Hawking-Page phase transition. Where at low temperatures, the free energy is dominated by thermal AdS₃, which we usually called basically the confined phase. And at high temperatures, the black holes dominate, and this is the deconfined phase of the theory. No. So in AdS₃, you don't have, well, it depends on the ensemble, but in the grand canonical ensemble, there's no small black holes. So that's also why the phase diagram is a bit different, and higher dimensions is more interesting. But if you turn on the angular velocity, there will be a version of this drawing, but there's no like small black holes. Now, if you go to a mixed ensemble, if I think in the microcanonical ensemble, there is a notion of a small black hole, but not at finite temperature. So in the canonical ensemble, there's no small black holes. But in microcanonical, there is. And for that, you have to see how the entropy is behaving. But yeah. So I'm not like the picture that you have here, it's pretty robust. Like I'm not hiding for you any like cool physics because I turn on angular velocity. Yeah. Good. Okay. Now, one thing to keep in mind, so maybe another thing that then you can write this as, so another way, written in equations, what this plot is telling you is that the free energy is -1/12, and it's pi squared C/3 over 1 over beta squared when beta is bigger than 2 pi, and then this is when beta is less than 2 pi, okay? So this is what we're getting by making this compromise of just looking at the semi-classical contribution of the free energy, what you get from just evaluating just the values of the on-shell action, okay? So that's nice. And the reason why I'm doing this is because we'll get back to this when we're doing the quantum theory, when we're doing AdS₃ CFT₂. And also because it connects very well. It's the baby version of like the more fancy phase transitions in higher dimensions. But yeah. Yeah, so when of course, you can vary with respect to various things, but because I want to see how the action responds to temperature, then I'm interested in looking at variations of the boundary metrics when I change the temperature.
How did you know that the boundary terms was the only relevant for the on-shell action?
Because by definition, if I vary the action, I get this stress tensor on shell. Like this is just, yeah. Because the bulk part, again, you don't get any bulk contribution to the stress tensor because it's the Hamiltonian constraint. And so then the variation of the action on shell can just be a boundary term. I'm evaluating an on-shell action. If you evaluate it off-shell, of course, then you have the bulk part, which are the equations of motion. But yeah. Yeah, so boundary actions in gravity, they're always boundary terms. Sorry, boundary actions, it's a tautology. Like on-shell actions in gravity, they're always just boundary terms. There's no bulk contribution to an on-shell, like, especially from the point of view of the variation, sorry, I should say. If you vary actions, then they're always boundary terms. Yeah. No, it's continuous, but the derivative is discontinuous. So this is straight, and this is a parabola. So you see, you have a constant, and then you have a parabola, so 1 over beta squared. So that's why this is a curve here. So there's a discontinuity in the derivative of the function. So maybe, yeah, so but then, yeah. So it's continuous, like these two functions, and that's why I said, like, if you put beta equal to 2 pi, the values of the actions are the same. But the dominant solution at like beta bigger than 2 pi, this is the dominant contribution. At beta less than 2 pi, this is the contribution. So what you're doing here, maybe also good to know, so this approximation, and it's also part of like what I'm doing here. If you want this result, you should only trust it when the couplings, so saying that you're only looking at this at the semi-classical level and suppressing quantum corrections, that means that C, which is 3L over 2G newtons, so it's basically something that controls the coupling constant in the theory. This basically is only valid in the limit that C is going to infinity. Okay? So that's why I only look at one of the exponentials. So in the limit that C is going to infinity, I only get this as the relevant contribution. The other one is highly suppressed. But then if I change the value of the temperatures, then this is the one that is dominant, and the other one is extremely, extremely suppressed. Okay, so when I do this plot, I'm plotting it with in mind as C goes to infinity. Okay? Okay, very good. So this basically graduates us almost from the classical point of view. The last thing that I wanted to say about the classical theory was just to draw a plot of what I have told you in terms of states in 3D gravity. So maybe let's draw it here. So or I should say a cylinder. So the solutions that we have found classically are the following. So I'll plot them as a function. I'll characterize them by how much mass and angular momentum they have. And actually, it's convenient to do L times M. So what we have found is basically one solution that we found was the solution where we had this at the value -1/8G, which was global AdS₃. And then the first black holes show up when the mass is equal to 0. And actually, black holes will only be black holes. So there will be here, all of this yellow region here are going to be my BTZ black holes. And these lines that I'm drawing here, this is the line ML equal to J. So yeah, now I'm realizing I didn't tell you, but maybe many of you know. What is this boundary? Extremal, right? Also, from the point of view of the geometry, if I go away from that, so over here I will get naked singularities. And so that's also why I put that boundary. So they're not regular solutions from the point of view of the metric. And then this line over here is just basically, it's the opposite one. So because J is negative, so it's again ML equal to the absolute value of J. We have this lonely thing here. I'm drawing this other line over here because, like, the things that you get in this area, the ones in yellow, so just to be, sorry, let me not draw this line in yellow because this is not, I do want to characterize things that are in yellow are things that are physical. But just out of curiosity, if you're curious of like, what would be smooth solutions out here. So over here, you'll get closed time-like curves if you look at solutions that lie in this regime. And over here, you're going to get what's called defects, conical defects. Okay, so there will be solutions that will carry some mass and angular momentum, but they're again not singular. So the only things, so yellow means smooth solutions. And everything else and the rest, there's some is a type of singularity. Okay? So if you put that the boundary metric has the topology of a line times a circle, these are the only like smooth classical solutions to AdS₃ gravity. So we have characterized the space of smooth configurations in the theory. Happy? Question? Yeah, well, it's a space of smooth solutions. We'll quantize it. Do you want to quantize it? Yeah, me too. Let's do that. Okay, let's do that. Okay, cool. Yeah, we'll do it. I'm not joking. It's my next chapter.
This is not entirely classified. I mean, you are in the.
No, but. Okay, sure, this is Euclidean like quantum gravity, but at the end, I just evaluated a classical action, so I didn't do it really. Like the only thing that is quantum in this equation is saying why a path integral should compute a partition function. But I didn't do it. This is not a quantum computation. Yeah, sure, fine. Yes, yeah, so, yeah. But it's not like Okay, I can't like, let me put it this way. This is not like, in the sense in which this is not quantum, is that I don't have any notion of like what are the microstates that I'm counting. There's nothing discrete in this computation. It's at the best, the wishful thinking that there is something discrete here. Wishful thinking, because I have not shown that to you. It's the wishful thinking that this exists, and therefore I'm entitled to take a thermodynamic limit. But I have not told you at all what is this sum, and this is my next chapter. Can we understand?
Yeah, but you are approaching at least in a semi-classical regime to what
Again, but you could object very easily, like you're not allowed to do that before you tell me what that sum over E is, right? It depends on, I'm very happy that you're very open-minded and saying like, I'm comfortable with like, sorry, this is great, this is very encouraging, but it always depends. When I give these lectures, I get either like the student that is like, oh, of course you had to do this, or like, no, why are you doing that? Like, nobody told you that you were allowed to do it. So again, like there's a lot of like, okay, let's fingers crossed, let's test it, let's see what this will give, let's assume that this thing is well defined and that it actually could be interpreted in terms of like summing over a Hilbert space, that basically this is a trace over a Hilbert space. There's a lot of like if, hopefully, fingers crossed, and this is the outcome. The thermodynamic limit of all of those wishful thinking is this. And now my task now, so now I'm going to be like, okay, I need to do a better job because there's a lot of ifs here. So now let's try to understand if we can really see, what am I counting? Where is this entropy coming from? What are we doing here? Is this really like a good Hilbert space? Is this really a good theory of, a good quantum theory? So let's see if this is really, let's try to understand if there's such a good picture. Okay, so, but I haven't, at this level of the discussion, the only thing I have done is basically give you a characterization of like solutions to the classical theory. And how to describe observables in the classical theory, how to describe energy, how to describe angular momentum. But yeah, but this is, it's all classical theory, and it's not really addressing the first, that's also why I wrote it in quotes, because I haven't done that, and that's what I want to do. And we'll see what are the puzzles that come here, okay? And then you'll ask me, you'll raise your hand again, and we'll yeah, and we'll chat again. Yes.
Can I ask you something else?
Sure.
In this computation, I guess. In this convening computation of the thermal partition function and the BT zeta partition function, there should be a version of this computation looking at a contour in the complex plane. Is there or no? I mean, usually when we do computation in the Euclidean path integral,
yeah?
we look at we look for a contour in a complex plane, right? I mean, you know if there is some version of this computation?
Yeah, probably, yeah. For this case, I don't have to, sure, you can say like there's some prescription of like, oh, how are you picking, like, why are these the saddle points of like some integration over the space of metrics?
Well, I mean, this is a solution of an equation of motion. You know this. You know of this because you are solving certain equation of motion, subject to some boundary conditions.
Yeah, there should be a
right?
saddle point approximation to this path integral.
Yeah, I mean,
so that's
true.
what, and that's where you should tell me what is the space, like what defines this integral here. And so I'm basically saying there will be such a definition where the classical solutions are saddle points to that integral.
Yes, that's true.
Yeah,
but
anyway. And that's all that's what goes from here to here. That there's some complex contour here for which these are the saddle points of that complex integration.
Where can I clearly see that the physical solutions will only be in that range and not in the yellow one? In the last class, you showed that they have a negative heat capacity.
No, this statement, you just look at the metrics, inspect the line elements, and you will see that the line elements have singularities. And here I'm just describing the types of singularities that the line element will have. There's nothing thermodynamic here. So if J is too big, you'll see, well, make it singular. I should be careful because there's no like curvature singularity, but there's a pathology in the line element.
But can you get rid of that? Because when
not
you have
with pure gravity, not classically.
Okay, so that's the type of singularity that exists outside of the any singularity that is not a curvature singularity is what you are referring to defects?
Defects basically means that you have like a cone.
Yeah. I know that, but
So that means that you will have like a delta function source in your curvature tensors. And so when you compute, if you carefully compute the Riemann tensor on these geometries, you will see that you will have a delta function at the tip of the cone.
But doesn't the same thing happen when you have a black hole? Or?
But it's covered by a horizon.
Ah, okay. So there's a defect, but not a horizon covering.
So these ones, like there's something funky happening in the interior, but it's covered by a horizon.
Okay.
That's okay. So this basically, I should say maybe these are the ones, like, because there's no curvature singularity, there's a notion of singularity, but I don't want to get into the deals of it, but this basically violates cosmic censorships. These are the ones that are not, but you basically see that you, from an observer at infinity, you will be able to reach or to be causally connected with something that is unphysical in the interior of the geometry. What horizons do is that they basically protect you from those pathologies. And so it's not like these Lorentzian geometries are completely like smooth everywhere, but the horizon protects you from them. So that's why we consider them still like smooth in that sense, regular. Yeah.
The Schwarzschild solutions are inside the cone, are J equals 0, or why we didn't consider them? Okay. That's the first question. The second, is there something that that guides you in the sense that you know that thermal AdS is you should only consider these two type of solutions? Why you know that there is no other point more down or?
You can inspect the solutions. It's important here that I'm imposing, you can change the topology of the boundary metric, and then you will find other configurations. So this statement is based on a boundary condition. And my boundary condition is like, what is the topology of G0? And so if you change this, then this picture changes, because you will be able to sort of fill up the geometry in different ways.
But in the fixed boundary condition, how do you know that there is not any other point below the thermal AdS?
You just look at the line element. It's the same question as Cielo was asking me. You just look at your solutions. Write a solution that has like negative, so you know that your the two basic like conserved quantities are mass and angular momentum. So start writing. Like nobody has been able to see anything else that is regular in this like space. Then you can also use some, well, in Euclidean signatures, it's easier to see that these are the only solutions that are regular. In Lorentzian signature, it's like, yeah, you just look at the line. Like, so we wrote down, so when I wrote down these line elements as a function of these like L plus and L minus, you start playing with these functions and see if there's any other choices of these functions that will give you a globally like smooth solution. And you will see that there's the only values of these functions that give you smooth solutions are the ones that either give you BTZ or AdS₃.
Okay, thank you.
Yeah. But again, like you do it by inspection. Like you just look at what you get, and it's like this is all that you'll find.
Yeah.
No?
No? Yeah,
Sure,
I could hear you. But yeah, you're asking if this thing has something to do with this thing.
Yes, I mean, especially the gap. I mean, since there's like a continuous phase transition, I would say that there shouldn't be like that gap. That's what I failed to connect these two plots.
There's a connection. It's not direct. I'll tell you more about it. It's not, yeah, let's talk about it on Friday. Because I think on Friday
Okay.
I'll be able to get to that point.
Okay.
But it's not, yeah, if you want the gap, you're seeing it here. Like if there were more solutions, you would have added like more things here in between. Like there would have been more exponentials in here. But there were not.
Okay.
But okay.
Okay.
Yeah.
You're kind of saying that taking the corrections, that gap is going
No,
to...
let's
okay,
Friday.
okay.
But yeah, there's a relationship between like getting a phase transition and this gap, but it's not, yeah. It's not necessary. It's a sufficient feature, but it's not a necessary feature. That's all that I want to say.
More of an interpretation question. So, you use the quantum path integral just as a tool to calculate something that is like statistical mechanical.
Yeah, I want to give this, like let's say I wanted to compute this, and I want to understand what this might mean physically. And going through this like little line of thought, I'm like, that computes the partition function.
Yeah, that I can accept for now, but I still have some difficulty interpreting this situation because from a statistical mechanics point of view, it seems that we are dealing with geometry microstates with fixed temperature because we are in the canonical ensemble. Is that correct?
Yeah.
But that seems a bit weird to me because when we consider geometry, like PTS or whatever, it seems that the temperature is a property of one geometry. But now we have an ensemble of geometries, but the ensemble also has a temperature. And
You just discovered the
confusing.
information paradox. What gives rise to this entropy? Like, yeah.
Yeah, I mean, I don't have the answer. but
Exactly.
like-
We have no, that's why it's not clear where the black hole entropy is coming from, because this is a single solution.
But, yeah,
I completely agree with you.
Okay.
This is like nerve-wracking. So, for instance, if black holes didn't exist, so let's say that black holes never existed, and I do this exercise, I would have gotten that the free energy is always just a constant. The entropy of this solution is 0. And then there's no puzzle. So if you compute the entropy for this constant free energy, you will just get 0 entropy, which is fine, right? It was just one solution. Damn it, black holes. Like, there was another solution. Its free energy is a non-trivial function of temperature, and then if you estimate what would be the thermodynamic entropy associated to that, it will be huge. It will be this area over 4G.
But so the point is,
But we don't know where it's coming from because, as you say, we just looked at evaluating one solution on shell. There was no coarse graining. Like, there was no, there's no, like, little things that I chopped up. Like, I didn't do this. And so it's a puzzle of quantum gravity.
so it's something like, oh, we look at one solution, it has temperature, it has entropy, this is weird.
Exactly.
Let's try to interpret this as an ensemble.
Yes.
To see if, okay.
And
okay.
my
I
life is
think I'm
devoted
following.
trying to understand that. Like,
Okay.
and I'm desperate. It's
Fair
hard. Yes, but this is the puzzle of quantum gravity in the context of black hole physics. Yeah. Where is this thing coming from? What are the little bits? And so string theory provides answers to that, to this. And I hope Kara was also teaching you about context in string theory, where we do have an understanding of what this is going on. But generically, if you don't have the aid of string theory, just by itself, it's very confusing what is going on and what makes this thing like consistent. Because it also could have been true, and I believe that in many cases, you're not allowed to do this. that it was wrong, but we'll see.
Thanks a lot.
No problem. Exactly. AdS₃ needs to account for this. Yes, yes, yes.
Doing something
Yes, 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 amazing, yes. The CFT needs to tell me what is going on, and that's why I'm going to very soon start doing AdS₃. We'll first still push the gravitational side, but then I want to see, no, if AdS₃ is the way how to understand quantum gravity, how do I get all of this physics from the CFT, knowing that the CFT does have a Hilbert space, it does have this discrete spacing, I know what I'm counting over, so where's this physics coming from the CFT? Excellent question, yes. Oh, no, please no. Ask Dio next week. So if you're here next week for Dio's class, ask him what happens, and he will tell you many things. Many, many things. And it takes a whole week for him to tell you what happens if you erase the A. It's very tricky. Yes. There was another. Me too. Quantum gravity is very confusing.
I have two confusions from my first year of PhD. That's a good point to ask. When people told me about the Bagnados metrics, they told me they had that arbitrary function else.
By the way, yeah, Robinson is calling, when you put this thing here, it's called the Bagnados metrics because Bagnados was the first one.
It was a
to write it down.
full function, but at the very end, BTC and just global AdS are globally defined.
Yes,
Probably.
so that's what this drawing is.
And the rest of possibility are not globally well defined.
Yes.
That's a good point. And the other is like, if I have a free scalar field, I can compute the entropy. And at that point, I don't think that I should just only use the stress tensor. But here, I only have the stress tensor. Sorry, I don't have the full theory here, so it's kind of confusing. In respect to more standard QFT
like
computations.
the only thing that you have access to, like, is like, oh, let's pretend that, like, you're just following Gibbons and Hawking and seeing, like, what would this tell you? Because, yeah, so you have the Bekenstein-Hawking computation of, like, oh, there's some entropy, and then this is trying to shed some light of, like, well, is that still hold if you take this picture?
But is there an example on QFT where I can only use the stress tensor to compute in a certain approximation these kind of quantities? Or
Yes and no, because I'll tell you what types of CFTs for which there's a sense of, no. Not from, if you open the big yellow book, no. Yeah.
That's why this is weird, like pure AdS₃ could be one of the reasons why it's kind of
Pure AdS₃, like, again, if the only solution that we would have had at finite beta was pure AdS₃, this is just telling you that you're capturing the physics of the ground state.
I meant like the theory, like pure AdS₃, like the action and the full action.
Full action of what?
I meant like in this context, since we only have like the stress tensor, the Bagnados, or the L plus minus, I don't have access to the other sector in comparison to higher dimensions. So it's kind of like in any first to be a mill, you have several sectors in the large N expansion, right?
Yeah.
But here there is just L plus and L minus. It's look a little incomplete.
We'll get there. Let me do some quantum stuff. Sorry, otherwise, yeah. Let's do some quantum stuff. No, not yet. Okay. Sorry. Go ahead. The duality tells you everything that you do in gravity should have a counterpart in CFT. So yes, the CFT also will have a low temperature and a high temperature regime. Yes. I'm not changing the theory, so I'm not going to be trading like the CFT. There will be, the promise of AdS₃ is that there's a single conformal field theory that will tell you all about like the gravitational dynamics on the other side. Yeah, there will be something. The CFT should also have that phase transition. Yes, it's a necessary requirement, based on this. Yeah. No, that's a yeah. Ready for quantum? Yeah. Yeah. Let's do quantum. Okay. No. I'm like, and all of you guys are like, no. No, it's great. Sorry, your questions have been really, really very good. So I'm very happy. Don't be discouraged by my sarcasm and silliness, please.
It's because you have talked so far about classical physics, right?
Yes.
But yet you have central charge over there, and is a quantum mechanical
If you want,
signature. Why is there?
The-
I mean, it shouldn't be there if it's classical.
No,
right?
just don't call it central charge. Just call it the ratio of the AdS radius over G Newton. Is that okay?
But in the CFT side, it
I
will
know.
be central charge.
I
right?
know. I know.
Yeah,
As I was talking, I think, well, Julio's not here in the room right now? No. Yeah. So this is a reflection that a quantum anomaly could be captured by a classical anomaly. I know, you like to think about quantum anomalies, but sometimes you can trade them for classical anomalies. And this is one of the lessons of AdS₃. It's not special to AdS₃, but it's one of the lessons. AdS₃ is a case where you can see, because of the strong, weak nature of the duality, you can see that something that was very quantum in the CFT gets translated to something classical in AdS. I know that it might contradict your understanding of anomalies from quantum field theory, but that was just, yeah.
Last thing, that boundary condition is flat because we are at the boundary, right?
I made a choice.
But it has to be a flat space, that choice over there.
Yeah. This is just like, so when I was writing the boundary metric, it's just that. So I'm just writing it in a fancy way. It's a line times a circle.
It's because in the future you're gonna talk about AdS₃ and
You can
at
modify
the boundary
this. It's just that
should be flat.
I don't gain anything by doing this for like some generic G0. So I'm just trying to be explicit and say, so when I wrote down the space-times, I made choices of boundary conditions, and I just made a choice that the boundary metric was flat. That's all. So I just want to be clear that when I do this drawing, it's based on some choices from the beginning of the lectures when I told you like, oh, I'm going to look at this class of geometries. Yes, so I made a choice there. And I'm following that choice. So I'm not modifying that choice, that's all. But you can. You can modify it, but I don't want to talk about everything. Because I do really want to talk about quantum gravity.
Okay, thank you.
Okay. Okay, so we have 10 minutes, I guess. Yes, roughly. 12 quantum minutes. Okay, so let's talk about AdS₃ quantum gravity. So the way that I'm going to tell this story, it's all new, it's everywhere. But the way that I'm going to tell you this story is along of the lines of what's known as the Maloney-Witten computation, okay? So we have done a pretty good job at describing like the classical theory. So now you might be brave and ask the question, to evaluate this thing, okay? Now, here, I'm going to, so I want to evaluate this path integral on AdS₃. And path integrals, when you write them, you have to specify boundary conditions on them, like similar to what I was telling you before. And so what we're going to do, we're going to try to do perhaps the most natural computation following what we already learned. We're going to basically do the Euclidean path integral. So let me say here, the gravitational path integral like this, where I'm going to fix that my geometries at the boundary have the topology of a torus, okay? Because these are the solutions, like the Euclidean BT set, and Euclidean signature was a solid torus. And so we want to basically ask the question, can we really quantify this? Okay, and I'm not, again, here at this stage, I'm not doing AdS₃. It's just basically the question, can we compute this? Okay. Now, why do we think we have access to this? So, one of the reasons why we think we have access to this, so why is this within reach? So, not obvious, and but one of the reasons why we expect this to be within reach is very similar to the wiggly lines that I was putting there, but here we can do a slightly better job. So basically, the reason why these two gentlemen said, like, let's try to do this computation, let's try to do it, let's try to evaluate this set of boundary conditions, is because if you take some very similar to Gibbons and Hawking, that perspective that the dominant contributions to the path integral are given by the sum over geometries, you can basically think, well, this path integral, in some sense, should be organized as sum over, and here, I guess I'll call it, just not to mix it with that notation, I'll put the 0 down. So the 0 down means that this is a solution. To the equations of motions. So the reason why they thought this might be feasible is because they thought this path integral should have a saddle point approximation, where in the saddle point approximation, there will be a contribution, and here I'm going to pull out a factor of c, just to make it explicit. But there should be a contribution, an expansion of this, where I will have the contribution of the action at tree level, but then I will have contributions to this that will come at one loop. Sorry, G0, I was putting it underneath. At 2 loops and therefore, so this will be and higher. And if this is true, if gravitational path integrals can be thought in terms of this saddle point approximation, so this is called the saddle point approximation to the, if this is an exact statement of a gravitational path integral, then in 3D gravity, we do have access, we know what the range of the sum should be. And so in 3D, we have the luxury, so the advantage of 3D, this is the luxury, the power of the symmetries of 3D is that we have control over everything that goes into this sum. Okay? In higher dimensions, we don't have that control. We do not know what all the solutions are, all smooth solutions are, given some set of boundary conditions. But in 3 dimensions, we do. And so you might say, let's push this. Okay? Let's try to do this computation where we will sum over all possible solutions given some boundary condition and not just include their classical contribution, but also do the loops around each geometry. Okay? See, I just pull out a power of G Newton just to see how, so C here is functioning, so C is again 3L over 2G, but you should think of it basically as like actions are weighted by H bar in the path integral. So I'm taking it as like as a way how to count how many powers of H bar I have. So 1 power of C is tree level, 0 powers of C is 1 loop, 1 over C is 2 loops. So it's a way that I'm just basically keeping track of this. Because here, if you want, what I'm doing is that when you write path integrals, sorry, there's a 1 over H bar in the path integral. That's all I'm. You're saying that it's I don't know. We're just going to try it. So what this gentleman said is like, let's see what happens to the sum. Let's try to evaluate the contributions and what is the result. Does it converge? That's a great question. But most importantly, like, well, part of the convergence, so their question was, okay, we think that we can evaluate this, but the jackpot, the thing that we're really aiming for, hopefully, and the big question, so let me write this in red because we don't know. This is all the point of it, and what they were asking was, is this really a trace over a Hilbert space of minus beta to the h? Well, this happened. They did not input this. They just said, we're going to do this computation. And if this is a good quantum system, then I should be able to interpret it this way. And that's why I'm writing a lot of exclamation marks and question marks, because we're trying to see if that's going to be true or not. We don't know. Yeah, that's what I spend, like, we know all the classical solutions. What's that? Yeah. So the saddle point approximation, again, means that you solve, it means that the path integral is controlled by evaluating solutions, evaluating the path integral around solutions, and then looking at quantum fluctuations around each of these solutions. So in a sense, like what I'm doing here, basically, if you want from the point of view of this equation, what we will be doing is writing G as a classical G plus a quantum fluctuation around it. And then what I'm doing is I'm putting this in here, and then why did I write G squared there? Who knows? Okay, that looks weird. And then what I'm doing in this expression is basically saying, we're going to insert this inside here and then expand in H, right? And so each power of like, as more gravitons you're exchanging, then you're going into higher loops. But then you should consider all possible values that you have for G0. And so that's why then I have the sum over G0. So this is basically your solution to the equations of motions, and this is your quantum fluctuation to that solution. Sorry, G0 within. Yes?
There's some hidden feature about the bandwidth unit in this kind of this line of argument?
No, it just, does it have that form? There's no boundary. This does not have to be necessarily, of course, the Hamiltonian in gravity is trivial, but it's the question of like, what would be the Hamiltonian danger? They're showing me danger down there, sorry.
Yes.
Yeah, based on this discussion here, it should be like some boundary type Hamiltonian, but I'm not going to assume that it's a CFT or anything. It's just like, is there some Hamiltonian? Is there some energy eigenstates? Like, does it, or if you want, we can write it this way. Like, does this thing look like this? And what would be the sets of E? So what is the sum over E? That's basically the question. But I'm in danger zone. I mean,
we are out of time, but yes, but you are more powerful than me. So if you want to continue, we can for 5 minutes. But I don't know if in 5 minutes you can. Now, do you want to continue or not?
No, I think this is a good ending point because what I have to do next is a bit more technical.
Yes, it's not 5 minutes, yes.
No, it's not 5 minutes.
Okay.
Based on the questions also, it will be like another 2 hours.
Okay, yes. Well, we will not find out today whether there is a Hilbert space trace that we can take.
It will take more than 5
probably
minutes.
tomorrow or not. We thank Ale. Yes.